Today we will see how to calculate the sample size for regression problems. So as we have done in other lectures, we will study when we want to compute the confidence interval for the slope of a variable, when we want to make a test on the slope of a variable, and we will study a special case of regression that is called logistic regression. So let's say that we are interested in determining what is the relationship between the concentration of nitrogen dioxide in air, that is an air pollutant, and the lung capacity measured as the forced expiratory volume in 1 second of children. So this relationship is studied in children. How many children do we need to study if we want to determine the coefficient of a linear regression between these two variables with a maximum error of 0.02 and a confidence level of 95%? Okay, so we want to make a relationship between the concentration of this pollutant and the lung capacity, and then it will be a linear relationship, and we want to construct this confidence interval for beta 1 with a maximum error of 0.02. As we haven't done the experiment yet, but to calculate the sample size we need to know a few things. The first one is the variance of this NO2. So we will have to rely in previous studies and see how variable the concentration of NO2 is. So it will be 3.83. The variance will be this one squared, and this is measured, this 3.83 is measured in parts per billion. And the residuals is even more problematic because we haven't done the fitting yet, so we don't know what is the variance of the residuals in our case. But again, we will have to rely on previous studies, so we expect the residuals to be 6.26 squared. So we see that we have a relatively large variation here compared to this one. Okay, then in general, this is our regression model, and then we can, for each one of these parameters, beta 1, beta 2, etc., we can have, so beta 0 is just the mean of all samples, or can be approximated by the mean of all samples. So what the interesting ones are the beta 1, beta p. So for each one, this is our estimate, this is the true value. So this difference divided by this ratio of variances is distributed as a t-student with a number of degrees of freedom, and the number of degrees of freedom is n, that is what we want to compute, minus the number of parameters that we have to estimate, that is p plus 1. So we may solve for the number of samples, and we have n that has to be larger than this, that we see that it is very similar to the Gaussian-like formulas, only so it has a term depending on the confidence level divided by the normalized effect size, and this delta is the error that we allow to have. So this would be the 0.02. And there is the difficulty here, that is that n appears on the left side and on the right side of the equation, so it is not easy to solve for it. But computers have iterative algorithms that can solve for this. Okay, so in this case, we have something like 3,600 individuals, and here is a help to compute the variance term that appears here in the equation. So this help. This can be, for instance, if the variable is a Gaussian xi, the predictor is Gaussianly distributed, it is simply the variance of that. It is simply the variance of that variable. But if xi is a continuous and uniform variable distributed between a minimum value and a maximum value, then this is the variance that you should use. And if it is uniformly distributed between a minimum and a maximum, but it is a discrete variable taking k levels, then this is the formula that you need to use. Okay, so then what about if we want to make a test on the slope? So let's say that we have the same problem as we had above, but now our problem is not constructing a confidence interval, but checking whether beta 1 is different from 0. So is there really a relationship between the lung capacity and this air pollutant for children? And we want to have a 90% of power if this beta 1 goes larger than 0.02. So what we need to do is simply to extend the previous formula, that was this one, this part. So we have to extend it with the statistical power term, and then again n appears on both sides of the equation, so it is not so easy, and we need about 10,000 children. So again, this is why do we need so many children? The reason is that we want to be very sensitive. So it is a very weak effect. It is the slope we see, it is very small. It is only 0.02 or even it is a small effect, and we want to be very sensitive. So at this very small relationship between the two, we already want to have a power of 90%. So that requires a lot of samples. Okay, so what about logistic regression? So logistic regression is less known in some domains. It is the common tool, but in many others much less known. Okay, so in logistic regression, instead of predicting the value of some measurement, so let us look at this again. So we are predicting what is the forced expiratory volume in 1 second from some predictors. So instead of predicting a continuous measurement, what we predict is a probability. So we predict this p prime. We will come to this later, but it is related to the probability of something happening, and this is linearly predicted from some predictors. Okay, so let us imagine that we are interested in determining the relationship between age and traumatic recidivism. So recidivism is old people tend to fall, and then once you have fallen at least once, what is the probability that you will fall again? So these repeated falls. So let's say that the average age of the geriatric population, the one that you are interested in, is 70 years old, and the standard deviation of that age is 4 years, and then at 70 years you expect that the probability of falling again is about 6%, and the mean was 70, so at 70 plus the standard deviation, that is 74, you expect that probability of 6% to go up to 10%. Okay, so and you want to find this relationship between age and probability of falling again. So this probability is modeled in this way. So the probability of falling again is 1 over this sum here, and this is an exponential function, and it is not so easy to deal with nonlinear functions. And then what we do is to transform this equation into this one. So we simply define p prime, that is the logarithm of p divided by 1 minus p. This is called the logit transformation. And then the logit transformation, so the logit of the probability, is just a linear function. So it is now much more easy to handle. And then if we want to detect whether there is a relationship between the probability of falling and the age, how many samples do we need to determine that relationship? And we want to have a power of 90% if the probability of falling again goes beyond 0.1 at 74 years old. Okay, so this is how the probability of recidivism looks like. So at 70 years old it is 6%, and then at 74 here we want to have a statistical power of 90% if it goes beyond 10. So here is well beyond 10. And then once you fit these parameters, beta 0 and beta 1, the probability may look like this. Okay, so we will use the standard Gaussian formulas, and we will have the confidence level term, the statistical power term, and then the effect size normalized. So what is the effect size? So the effect size is something a bit complicated. It is the logit, it is the logarithm of two ratios. And the first ratio is what is the expected probability at mu, so at 70 years old. And the other one is what is the probability of at 74, what is the detection that you want to have, the detection power that you want to have at 74. So this doesn't mean that this will happen. It may happen or it may not, but if it goes beyond this probability, you want already to have this 90% of probability of statistical power. So this is the normalized effect, and then it is normalized by the probability of falling at 70 years old. So in this particular case, this delta is like this, and then the sample size is about 500 people. So you need to study 500 people in this range of a geriatric population whose mean is 70 years old. So you will have fewer people, more people. So a younger person, younger people or older people, and then you will have to study how if they have had a recidivism in, let's say you have to fix a period, so let's say in 1 year, and then you will be able to make this fitting. You will be able to make this fitting, and then with that number of people you will be able to say whether beta 1 is larger than 0 or not. So this would be all for regression. So what we have seen is that we can calculate the sample size using more or less the kind of Gaussian-like formulas that depends on the confidence level, the statistical power, and the normalized effect. But the way to normalize is different for each one of the cases, and we have to rely on previous experiments to be able to calculate the sample size, because otherwise we wouldn't know what is the residual variance, the variance of the predictor variable, and the same for the logistic regression. And this would be all.